In this video, we're going to talk about probably one of the most useful gas laws, the combined gas law. This is great for when you have changing conditions, but the number of moles of gas that you have in your container remains constant. Pressure is proportional to volume. What we saw is P1 times V1 is equal to P2 times V2. That's Boyle's law. We have Charles's law, which states that V1 over T1 is equal to V2 over T2. And then we have Gay-Lussac's law, which says P1 over T1 is equal to P2 over T2. I can combine all three equations into one handy-dandy little package. P1V1 over T1 is equal to P2V2 over T2. So we can use this to determine the effects of changing two factors on a third factor. That means we can do all sorts of cool problems, but that's not the only reason that this is probably the most useful of the gas laws. The most useful of the gas laws is because if you're missing any one of the three factors, assume it's a constant and drop it from the equation. This means you can always do a Boyle's law problem using the combined gas law. You can always do a Charles's law doing the combined gas law. You can always do a Gay-Lussac problem using the combined gas law. It's wonderful. So let's take a look at those three possibilities. Example, if we have pressure at constant. In other words, if our problem doesn't actually state the pressure, assume it's constant. So here's our example. A 3.0 liter sample of a gas was heated to 350 Kelvin. If the temperature of the gas was initially 298 Kelvin, what volume did the gas occupy initially? So this is dealing with volume and temperature. So what type of law are we talking about here? We're talking about Charles's law. So volume 1, temperature 1, volume 2, temperature 2. So let's start filling in our variables here. It says a 3-liter sample of gas was heated to 350 Kelvin. If the temperature of the gas was initially 298 Kelvin, so the temperature of the gas was initially 298 Kelvin, that means that the temperature final must be this 350 Kelvin, and the volume final must be that 3.0 liters, because they're asking what did the volume occupy initially. So V1 is equal to a question mark. So V1, I don't know. V2 is the 3.0 liters. T1 was 298 Kelvin, and T2 was equal to 350 Kelvin. Remember, pressure wasn't mentioned, so I don't have to worry about it. So if I use the combined gas law, P1 V1 over T1 is equal to P2 V2 over T2, and pressure was never mentioned, we cross it out. That leaves us with V1 over T1 is equal to V2 over T2. I'm looking for V1, so I'm going to multiply both sides by T1, so I get V1 is equal to V2 T1 over T2, and if I plug in all those numbers, I see that my temperature in kelvins cancels. I'm left with a volume unit of liters, which you really can't see too well, but the answer to this problem is then 2.6 liters. Does this make sense? The gas had been heated. It expanded to 3 liters. That means it had to have been less than 3 liters to start with. And we didn't double the temperature, we just raised it up 52 degrees, so we're not expecting a doubling of our volume. So this is a reasonable answer. So what happens if I drop volume? So an example like this would be a gas at 298 Kelvin has a pressure of 2.4 atmospheres. What is the pressure of the gas if it is heated to 800 degrees C? So what have we got here? We've got pressure and temperature. Volume has been dropped. It's not made a mention of it, so we assume it's constant. We drop it from our equation. So P1, T1, we need a P2 and a T2. So pressure 1 was the 2.4 atmospheres. The temperature 1 was 298 Kelvin. And then it says what is the pressure of the gas? So I don't know what that is. If I heat it up to 800 degrees C. Now that's degrees C. I need to make sure that it's in Kelvin. So I'm going to go ahead and add my 273. That brings me to 1073 Kelvin. So I've got my variables listed out. My equation, combined gas law, P1 V1 over T1 is equal to P2 V2 over T2. If my volume isn't mentioned, we assume it's constant, we cancel it out. I get P1 over T1 is equal to P2 over T2. What type of equation is this? What law is this? Gay-Lussac's law. I'm looking for P2, so I'm going to multiply both sides by T2. T2 cancels. I get P1 T2 over T1 is equal to P2. Now I can plug in my numbers. I got 2.4 atmospheres times my T2 is 1073 Kelvin divided by 298 Kelvin. That's my T1. And I see that the pressure is 8.6 atmospheres. I more than doubled my temperature in Kelvin, therefore I should have more than doubled my pressure, and in fact I did. I actually tripled my pressure, almost. And so in our next example, we're going to drop the temperature. If temperature is not given, assume it's a constant. So in this example, a 3.0 liter sample of a gas was at 2.5 atmospheres. If the gas is allowed to expand to a volume of 1 times 10 to the 4th liters, what pressure would it exert? All right, so I've got pressure, and I've got volume. Pressure 1, volume 1. Pressure 2, volume 2. So a 3 liter sample of gas was at 2.5. So 2.5 atmospheres and 3 liters, 3.0 liters. Pressure 2, what pressure would it exert? I don't know. What is the volume? 1.0 times 10 to the 4th liters. So let's get cracking at solving this problem. So I've got my variables laid out. If I've got P1 V1 over T1 is equal to P2 V2 over T2. Temperature is not given, so I assume it's constant, ignore it. That gives me P1 V1 is equal to P2 V2. What type of law is this? That's a Boyle's law. So P1 V1 is equal to P2 V2. I want to find P2, so I'm going to divide both sides by V2. That cancels, and I get P1 is equal to P2, not P1. We get P2 is equal to P1 V1 over V2, which is equal to the 2.5 atmospheres, times our volume 1, which was 3.0 liters, all over 1.0 times 10 to the 4th liters. And when we do the math, we get 7.5 times 10 to the minus 4th atmospheres. A very, very small pressure. But that makes sense because we've expanded to such a large volume. Now, what if we have all three variables? This is where the combined gas law is really good. So in this example, a 3.0 liter sample of gas at 2.7 atmospheres was heated to 350 Kelvin. If the temperature and pressure of the gas was initially 298 Kelvin and 28 atmospheres, what volume did the gas occupy initially? So I'm going to have a P1, I'm going to have a V1, I'm going to have a T1, I'm going to have a P2, a V2, and a T2. So P1, we want to know a 3.0 liter sample of gas at 2.7 atmospheres was heated to 350 Kelvin. If the temperature of the and pressure of the gas was initially 298 and 28 atmospheres, so 28 atmospheres and 298 Kelvin, what volume did it occupy initially? So that means my V1 must be a question mark. So my P2, my V2, and my T2. P2 must be 2.7 atmospheres. The volume 2 is 3.0 liters, and the temperature 2 was 350 Kelvin. So some unknown volume of gas at a really high pressure and a lower temperature is allowed to expand to 3.0 liters and 2.7 atmospheres at 350 Kelvin. So there's a lot of stuff going on here, but we've nailed down all of our components. Now we just have to make sure that we use our combined gas law and rearrange properly. So we got our variables all laid out, and we use our equation P1 V1 over T1 is equal to P2 V2 over T2. This time we don't get to drop anything. Everything has changed. So I want to find V1. I'm going to multiply both sides by T1 over P1. T1 over P1. Look what that does. T1 cancels. P1 cancels. So V1 is equal to P2 V2 T1 over T2 P1. And if I plug in my numbers, when I have that all plugged in and do the math, I get the initial volume to be 0.24 liters. Actually, I lied. It should be 0.25 liters because I have to round up for the sig fig. So 0.25 liters. Now, you can use the combined gas law, as we've shown, to do Boyle's law, Charles's law, and Gay-Lussac's law. And it's also very important if you have all three variables and you want to be able to determine either the final or the initial pressure or volume or temperature of any one gas setup. From here, you should move on to the next gas law we're going to talk about, and that is Avogadro's law.